Hi, in this video we'll look at how to attack an AI model. Generally, AI models are trained using data and they perform well after the training has stabilized. The concept of adversarial attack is that an adversary is interested in modifying the neural network such that it generates wrong outputs. In many cases, these take the form of imperceptible perturbations that are added to an image and cause the network to generate misclassified outputs. Two common forms of attack vectors are white box attacks and black box attacks. White box attack model assumes that the attacker has full knowledge and access to the model, whereas black box attack assumes that the attacker only has access to the inputs and outputs of the model but not the internals of the model. FGSM or fast gradient sign attack is a white box attack model. As we saw in one of the previous videos, the way AI model learns is by adjusting the model weights to minimize the loss based on the backpropagated gradients. The FGSM attack model similarly adjusts the input data rather than the model weights to maximize the loss rather than minimizing it based on the backpropagated gradients. More detail about this model is available in this paper. Let's look at an example output of such an attack. On the left, we see in the image of a panda, and to this image, if we add an imperceptible perturbation as shown by this image in the middle, and we scale it by an epsilon value of 0.001, and we add this image pixel wise to this image, we get the output result on the right hand side. When the image on the right hand side is sent to the same neural network that was originally trained to classify this left image as a panda, it turns out that the model thinks that the image on the right is a gibbon and not a panda, and also the model is overly confident that it's a gibbon. So the confidence is increased from 57% being panda to 99% it being a gibbon. So let's see how we can generate an attack of such form. We do our usual imports. On the input side, we have a set of epsilon values. These are the scaling factors that are used to scale the amount of perturbation added to the input image. We use a pre-trained model from the Linnet network that has been trained on the MNIST dataset. Then we recreate our model class. This model consists of two convolutional layers, two dropout layers, and two fully connected layers. The forward function of this class takes in an input x, passes it through all the individual layers, and generates the output. In terms of test data, we use a test loader, which is a data loader, and pass it to it the MNIST data set, and we apply two transforms to the data. First, we convert each input sample to a tensor, and we also normalize the tensor using the mean and standard deviation values given here. As an example, if we get the first example from this test loader, we see that it generates two outputs, x and y. X is the image, which is of shape 1 by 1 by 28 by 28, wherein the first one is the batch, the second one is the channel, number of channels being 1, and then 28 by 28 is the number of pixels in the MNIST dataset for each image. Y is the corresponding label for this first example. We choose the device. Ideally, you would have a machine with a GPU, but in this case, I have a machine with a CPU. So the training will be slower. First, we initialize the model given by the model definition above. We pass it to the device. We load the state dictionary from the pre-trained model weights that we had set the path to previously. We map it to the device. Then we set the model to evaluation mode. Focusing on the FGSM attack, the attack function needs three inputs. First is a clean image that we want to perturb. Second, epsilon is the pixel-wise perturbation amount or the scaling factor that we need to apply. And third is the data gradient or the gradient of the loss with respect to the input. That can be seen here where we are computing the gradient with respect to x, which is the input, of the loss function j, where j is a function of the network parameters theta. The output of this function is a perturbed image, which is essentially the summation of the image along with epsilon times the sign of the data gradient. So in code it looks like this. We take the sign of the gradient, we take in the epsilon value that was passed in, multiplied by the sign of the gradient, add it to the image, and out comes the perturbed image. And then we clamp the perturbed image in the 0 to 1 range and return it. We also need a denormalization function which removes the normalization that was applied as part of the transform in the data loader. In the test function, for each sample in the test set, we compute the gradient of the loss with respect to the input data, which is data grad. We create the perturbed image by calling the FGSM attack function, which gives us perturbed data. And then we check if the perturbed example is adversarial or not, which means that whether it has been misclassified or not. Looking into the test function in detail, we loop over the x and y from the data loader. In this case, it's a test loader. So we have each image stored in data and the corresponding label stored in target. We move the image and target to the device. We set requires grad equals to true so that we compute the gradient with respect to the input. We generate the output of the model on this data by doing the forward pass. We get the initial index of the predicted label for that data. If the initial prediction does not match the target prediction, which implies it's already a misclassification, so we don't bother attacking it further. Otherwise, we compute the loss, zero out all existing gradients, calculate the gradient of the model in the backward pass, and then store the gradient of the input in the data grad variable. We then do the denormalization of the data and then call the FGSM attack function by passing in this denormalized data, the epsilon scaling value, and the data grad, which is the gradient of the loss function with respect to the input. What we get out is the perturbed data, which is the modified image or the modified data after it has been attacked using the FGSM attack function. We then reapply the normalization by calling the transform.normalize with the same mean and standard deviation values, and then reclassify this perturbed data by passing it through the model and generating the new output. And then we check for success by looking for whether the predicted output matches the target output or not. If it does not match, then it implies that the adversarial attack has been successful, and we store few adversarial examples to view later on. We calculate the accuracy using this epsilon value over all the samples, and then we return the final accuracy and the sample set of adversarial examples. Finally, we call the test function by running the attack on the different values of epsilon, and for each epsilon, we get back the accuracy and the set of adversarial examples, which we store in a list of accuracies and examples. Next, we plot the accuracy of the model against these different epsilon values. What this graph shows us is the accuracy versus epsilon plot. This indicates that as the amount of epsilon increases, which is the amount of perturbation that has been added, which is a scaling factor, the accuracy of the model decreases as we would expect it to be. One thing to note is that the decrease in accuracy is not linear, as in it does not decrease by the same slope as we increase the epsilon, but there is a strong non-linearity behavior in the decrease in accuracy. So somewhere the model reaches the accuracy of 0.1, which is the same as a random guess for 10 classes. Next, we look at some of the adversarial examples that have been generated and plot them in a figure. Each row here corresponds to different epsilon values, where epsilon equals to 0 implies no perturbation has been applied, which is why the predicted label matches the target label. As we keep increasing the epsilon, we can see that there is a small amount of perturbations that have been added to the input. And if we look at this example, the true label of this image is 3, but after perturbation, the image has been misclassified as label 2. Similarly, for this example, the original image label is 4, but after perturbation, it has been misclassified as 9. As you can see, as we increase the epsilon values, the amount of noise keeps increasing in the image, and it's no longer imperceptible, and at large epsilon values, the noise starts becoming extremely powerful and visible in the image. This is one form of attack, the FGSM attack. There are other ways to attack the models and generate adversarial outputs. That's it for this video. See you in the next one.